Yo, what's up coders? Welcome back to another deep dive into the world of programming. BB here, ready to break down how your code actually runs. Ever wondered what happens after you hit that run button? It's like magic, but with less smoke and mirrors, and more ones and zeros. The process is fascinating and crucial for every coder to understand. We write code to tell computers what to do, but they don't speak Python or Java directly. They need a translator to understand our instructions. They vibe with machine code, a language of pure numbers. This is the only language they truly understand and can execute. That's where execution comes in. It's about transforming your code into something the computer can understand and execute. This transformation is key to making your programs work. There are three main ways to do this, each with its own unique approach and benefits. Compiled languages. Think of this as translating your whole book into another language before giving it to someone to read. The entire code is converted into machine language at once. C is a prime example. It's efficient and fast because the translation happens beforehand. Interpreted languages. Imagine reading your book aloud to someone, translating each sentence on the fly. This means the code is executed line by line. That's Python in a nutshell. It's flexible and great for scripting and rapid development. JIT-compiled languages. This one's a mix, like translating a chapter at a time, right before it's read. Java rocks this style. It combines the best of both worlds. Let's dive into each approach, shall we? We'll explore how they work, their pros and cons, and when to use each one. Let's kick things off with compiled languages, the OG way to run code. These languages have been around for decades and have stood the test of time. Imagine you've written a killer game in C, a classic compiled language. It's a language that has powered everything from operating systems to game engines. Before you can unleash your masterpiece, you've got to compile it. This step is crucial because it transforms your human-readable code into something the machine can execute. A compiler is like a super strict translator that takes your entire C code and transforms it into machine code all at once. It checks for errors and optimizes the code for performance. Think of it as turning your code into a language your computer's processor can directly understand. This direct execution is what makes compiled languages so powerful. Speed demon. Since the code is already in machine language, it runs blazing fast. This is why many high-performance applications are written in compiled languages. Efficiency master. Compiled code is optimized during compilation, making it lean and mean. The compiler removes unnecessary instructions and streamlines the code. Platform specific. Code compiled for Windows won't run on Mac OS without recompiling. This means you need to compile your code separately for each platform you want to support. Debugging woes. Finding errors in compiled code can be trickier, like trying to find a typo in a translated book. The compiler might catch some errors, but runtime issues can be elusive. Despite these challenges, the power and efficiency of compiled languages like C make them indispensable tools in the world of software development. Now, let's hang out with interpreted languages. They're all about keeping things chill and flexible. Picture yourself writing a script in Python, the king of interpreted languages. Instead of a compiler, Python uses an interpreter. This buddy reads your code line by line, translating and executing each instruction on the spot. It's like having a conversation with your computer, more interactive, less formal. Platform-independent Python code runs on any machine with a Python interpreter installed. Write once, run anywhere. Easy debugging. Since code is executed line by line, finding and fixing errors is a breeze. Slower execution. Interpretation adds overhead, making it slower than compiled languages. Runtime errors. Some errors only pop up during runtime, which can be a pain. Now for the cool kid on the block, JIT-compilation, the master of balance. This technique is a game changer in the world of programming languages. Java, the poster child for JIT-compilation, takes a two-step approach that combines the best of both worlds, interpretation and compilation. First, your Java code is compiled into an intermediate language called bytecode. This bytecode is platform independent, making it highly versatile. This bytecode is like a universal language that can be understood by any machine with a Java Virtual Machine, JVM. The JVM acts as an interpreter, translating bytecode into machine-specific instructions. When you run your Java program, the JVM's JIT compiler kicks in. This is where the magic happens. It analyzes your code and selectively compiles frequently used parts into machine code on the fly. This dynamic compilation boosts performance significantly. It's like having a translator who memorizes common phrases for faster communication. The more you use certain parts of your code, the faster they get. Portability and performance. Java achieves both portability, thanks to bytecode, and decent performance, thanks to JIT compilation. This dual advantage makes Java a popular choice for cross-platform development. Adaptive optimization. The JIT compiler continuously optimizes code based on runtime behavior. It learns and adapts, making your program run more efficiently over time. Startup latency. The initial compilation process can cause a slight delay when you first run your program. This is a small trade-off for the performance gains you get later. Complexity overload. The JIT compilation process can be complex, making it harder to understand and debug. However, the benefits often outweigh the challenges, especially for large-scale applications. Section 5. Advantages of compiled languages. Speed and efficiency. Compiled languages are like finely tuned sports cars. They're built for speed and efficiency. Since the code is converted to machine language upfront, there's no need for on-the-fly translation during execution. This direct execution translates to lightning-fast performance, making compiled languages ideal for resource-intensive tasks like game development, operating systems, and high-performance computing. Moreover, compilers are optimization masters. They analyze your code and apply various techniques to make it run faster and use less memory. Section 6. Disadvantages of compiled languages. Platform dependence and debugging. While compiled languages excel in speed, they come with a couple of drawbacks. One major limitation is platform dependence. Remember, machine code is specific to the computer's architecture. This means if you compile your code on a Windows machine, it won't run on a Mac OS or Linux system without recompiling it for that specific platform. It's like trying to fit a square peg in a round hole. The code just won't work without adjustments. Debugging can also be more challenging in compiled languages. Since the entire code is translated at once, pinpointing the source of an error can be like finding a needle in a haystack. Section 7. Advantages of interpreted languages. Flexibility and ease of use. Interpreted languages are like trusty Swiss Army knives. They're versatile, adaptable, and easy to use. Their biggest strength lies in their platform independence. Remember, interpreters execute code line by line, translating on the fly. This means you can write your code once and run it on any machine that has an interpreter for that language. It's like having a universal translator that lets you communicate with anyone, anywhere. Interpreted languages are also beginner-friendly. The interactive nature of interpreters makes it easy to test code snippets on the fly, experiment with different approaches, and learn the ropes of programming without getting bogged down by compilation steps. Section 8. Disadvantages of interpreted languages. Performance overhead. While interpreted languages shine in flexibility and ease of use, they often lag in the performance department. The on-the-fly interpretation process introduces overhead, making them generally slower than their compiled counterparts. Imagine having to translate every sentence of a book as you read it. It would definitely slow you down. Similarly, interpreters have to do this for every line of code, which can impact performance, especially for complex or computationally intensive tasks. Another downside is that some errors might lurk undetected until runtime. Since interpreters check code line by line, errors in later parts of the code might not be revealed until those lines are executed.